On example 10, a state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk. If T is measured in years, the growth rate of the elk of the population is dp dt is equal to kp times 1 minus p over 4,000 between 40 and the population between 40 and 4,000, right? That population interval makes sense because the initial population it said was 40, and then they said that the carrying capacity should be 4,000. Number 1, write a model for the elk population in terms of T. All right, so then we'll have to do something similar to what we did on example 9. We'll have to turn that logistic differential equation into its just straight up logistic equation and do some algebra up on that thing. On number 2, use the model to estimate the elk population after 15 years. Very simple. Just plug in 15 when we're done. Number 3, find the limit of p as t approaches infinity. Is that it on this particular question, or do we have another part? I think we have one more. Number 4, find the time when the rate of the population growth is at its fastest. So most of the parts of this question are very similar to the previous one. The biggest difference is going to be that very first one, let me go back, where we're actually writing the model. And the reason why it's going to be different is the fact that we don't have k. That's not a number that we have. We had it before. We're going to have to solve for it. And in order to solve for it, you need another point, which is why they said after 5 years, the elk population is 104. All right, so now I think that we've got a pretty good grasp of what the heck is going on here. Let's go ahead and try to solve this. Our differential equation, dp dt, is equal to, I don't even know what, times p, 1 minus p over 4,000, or 4,000 being our carrying capacity, of course. Carrying cap. All right, and then a couple of other things I'm going to write down, and that's, let's just write this as ordered pairs, 0, comma 40. I think it started with 40 elk, yes. And then 5 days later, 5 years later, not 5 days later. My gosh, that'd be fast. They're not rabbits. 104. Oh, okay. Just turn it into 140 again, why don't you? There we go. All right, so let's go ahead and write our equation like we did in the previous question. Number 1, we've got our population should be equal to its carrying capacity of 4,000 over 1 plus our b. Okay, we don't know that either, do we? Can we solve for it? I think we can. E to the negative k, now that one we don't know, times t. All right, so let me show you an example of a time of, I don't remember the little formula for b. Well, that's okay. If we don't remember it, all we have to do is use the initial condition that's right there, and then we can easily solve for it because the e to the stuff is going to cancel out. So let's do that. P of 0 should be equal to 40. And now let's just go ahead and plug in a 0 for our t. 4,000 over 1 plus b e to the negative k times 0, which is going to be 0. So that part is going to disappear because e to the 0 is 1, and I just have 4,000 over 1 plus b. Okay, I'll cross multiply that, and when I cross multiply that, I have 1 plus b is equal to 4,000 over 40, cancel some stuff, and I have 1 plus b is equal to 400 divided by 4, otherwise known as 100, and then b is equal to 99. Probably could have guessed it. All right, so then, so far our equation is p of t is equal to 4,000 over 1 plus 99 e to the negative kt. Now the next thing I need to do is use the second point that they gave me and plug that in, this time for both p and for t, and then use that to solve for our k value. So p of 5 is equal to 104, which is 4,000 over 1 plus 99 e to the negative 5t? Yeah. Yeah, that should do it. And again, cross multiply once again. I've got 1 plus 99 e to the negative 5t. Wait, I'm solving for k. It's not a t. Here, change that. Negative 5k. Easy fix is equal to whatever 4,000 over 104 simplifies. And you know what? The calculator's going to simplify that for me. 4,000 divided by 104. And we get 500 over 13. Of course. Okay. I need to subtract 1. 99 is 99 e to the negative 5k is equal to, I need to subtract 1 from that. That's going to be like 13 over 13. And that would give me 487, I think, over 13. And now divide it by 99, or in other words, multiply it by 1 over 99. So I just need 13 times 99. That's a 7, a 2. That, this, 7, 1, 1, 1, 2, 8, 7. So I have e to the negative 5k is equal to 487 over 1,287. Sorry, this just seems weird. Let me just double check my math, my arithmetic. All right, so subtract 1. Bam, that looks right. And then divide by 99. Okay, that was right. Okay, and then as we've done 4,000 times before, let's just go ahead and take the natural log of both sides. Negative 5k is equal to the natural log of 487 divided by 1287. Divide by negative 5 to get our k value. Natural log 487 over 1287. All of that divided by negative 5. That is certainly a calculator issue. All right, so we already have that number. We want to take the natural log of that number. Natural log of... I think that's in here, second answer. Yeah, awesome. And then divide that by a negative 5, and let's approximate that. And we have 0.194. Now, whenever I'm doing calculations on this, I want to use that whole entire thing. So let's go ahead and store that. That's under the vars menu. I'm going to hit store as, we'll just store it as A. Okay, so 0.194, that's what I'm going to write, at least on my paper. So K is about 0.194. All right, so one last time. P of T is equal to 4,000 over 1 plus 99 e to the negative 0.194 t power. And we have finished, finally, part A. And by part A, I mean part 1. All right, what was the second part of this? It asked us use the model to estimate the population of the elk after 15 years. Okay, that's going to be fairly simple. But like step number 1, change your color back to blue, or else people are going to laugh at you. Number 2, I just want to find P of 15. It does. Okay, so I'll plug all of this into the calculator, of course, and it will look sort of like this. Boop. I have fraction 4,000 over 1 plus, our b value was 99, e to the negative a, because I stored that in as a, times 15. And let's approximate. Our number of elk is 628. I'll go ahead and write 629. We'll give that 0.5. It's not half an elk. We're just going to go ahead and say that's an extra elk. So we've got 629 elk. Approximately 629 elk. Number 3. Number 3 asked us to find the limit of P as t approaches infinity. Limit t approaches infinity of this P of t function is equal to 4,000. Why is it 4,000? That's its carrying capacity. That's as big as that population can possibly get. Carrying cap. And then the last part, I do believe, asked us at what time, so this one's a little bit different, at what time in how many years is the growth rate the fastest, right? Find the time when the rate of the population growth is at its fastest. So this takes it a little bit different direction than the previous one. So our population is going to be half of 4,000. So we got 2,000, of course. And now we're just going to set that equal to our equation and then algebraically solve that. Hopefully there's enough space here. If there's not, I'll just add a page. It's cool. So 4,000 over 1 plus 99 e to the negative 1 point. No, it isn't. Switch that around. Negative 0.194. Again, a times t, and we're solving that for t. Let's cross multiply. 1 plus 99 e to the negative 0.194t is equal to, and I divide that by 2,000, I'll just get 2. Subtract over, I'd get 1. 99 e to the negative 0.194t is equal to 1. Divide by 99, e to the negative 0.194t is equal to 1 over 99. Take the natural log of both sides. Everybody knows that needs to be in pink, though, or else people will laugh at you. Negative 0.194, okay, all right, whatever, is equal to the natural log of 1 over 99. And then finally, divided by negative 0.194, divided by negative 0.194. Calculator time. Okay, it was... Now I've already forgotten. Natural log 1 over 99. That's right. Natural log of 1 divided by 99 divided by negative, and then use our a value that we have already stored in there and approximate that. All right, so we've got this about 23.642-ish years. I'm going to go ahead and store that as b just to verify that this actually makes sense. Store that as a b value here. Because now if I plug that into our equation, remember that that should give us, it should give us half of the population, which was 2,000. So I'm just going to copy this one here if I can. Okay, no. Yes, copy. And then come down here. And then I'm going to paste that one, and then right there where it says 15, delete that out, and then times by b, and hit enter. I'm not even going to approximate this one. I'm just going to hit enter, because yes, it is exactly 2,000. All right, 23.642. T is approximately 24.642. 642, yes. Now, here's the thing, folks. I have been pretty much just telling you that this happens at half of the carrying capacity, and you've kind of taken my word for it. We've seen it in graphs or whatever. We saw it with the cookie epidemic. But what I would like to do in one last video and then wrap the whole thing up with some facts about logistic growth is actually to show you the math that the fastest growth rate happens when your population is at exactly half of the carrying capacity.